Yeah, thanks so much. Thanks everybody for joining. So in this talk, I want to talk about photolistic avatars. So in principle, there's a very simple vision behind it. Basically, I want to make sure that we can do what you're doing right now in this setting in a virtual setting. So I want to capture somebody and want to make sure that this capture, this virtual representation, is indistinguishable than the real person, at least from a visual standpoint. I mean, there's other things like how you talk and how you speak, but at least from a visual standpoint, the idea is, okay, you want to get some sort of visual input, you want to get a representation, and this one should be completely indistinguishable from the real world. And the future of this hopefully will be that we have better versions of Zoom, we can insert ourselves into a movie, we have movie quality in games, we can generally digitize ourselves, and we can have our virtual copies also interact with each other. And maybe in the future we'll have a seminar like this, where we are in different places, but it looks like as it does today. So how do we get there? So the idea of having avatars like this, generally speaking, is not new, right? Many people have tried this, and there's obviously a lot of work in this area. So I'm going to go a little bit back in time. I don't want to go to the current state yet. I want to talk a little bit about what graphics researchers have been doing, like for the last 3 decades or so. And what avatars in graphics were mostly parametric face models. This is actually very basic. So the idea there is you have a bunch of 3D scans of a person. You take all these scans together, and what you do is essentially you compute a lowering approximation with the PCA of the human face. And what that means in practice is you see here, you see a bunch of these sliders on the right-hand side. So these are the PCA coefficients. A little bit more than just PCA coefficients, but on the high level, that's mainly it. And the idea is with these parameters here, so you have 6 for the rotation and inflation, you have the shape identity here, so you see how the size changes. You have 80 of these coefficients here. You have a bunch of them that change the albedo and the reflectance, and you have a bunch of them that change the expressions. And the idea is that basically with these parameters, with this low-rank approximation, you can parameterize ideally all types of human faces. And these blend shapes, what they're called, they're being very widely used. This is what I'm saying is like the precursor to a photolistic avatar. And people have been using this in the movie industry, in the game industry, for, again, quite a while. And this is de facto the standard how you animate and also render human face. Doesn't look very realistic yet, but it's already, you have pretty good control already, right? So you can change a bunch of these coefficients, and you can change the faces on top of it. You can even add illumination. So this is a sort of harmonics parameterization for the lighting here, right? And what you get is, if you're summing up all of these parameters here, so there's different versions of how many exactly you use, but you roughly have on the order of like 100, 200 parameters here, you can essentially define how the image looks like of a face, right? So assuming you have a rendering process in between at some point, you take these parameters get you to a 3D model of a face, you have a rendering process, and you get an image out of it. And these parameters P, with an image formation model, define how the image should look like. Again, we have geometry, albedo, expression, illumination, and pose. And we can use that for rendering. But we can also go ahead and do the inverse process. So we can kind of go from a graphics feed-forward application, we can go to a computer vision application, where now we have some input data. In this case, we want to use some RGBD data. This is from a Kinect. So you the depth data you see on the top, you see the RGB data on the bottom. And you can formulate this as an optimization, as an energy minimization, to solve for these parameters P, given these observations. And you want to make sure that your model that you're rendering then looks like these observations, right? So it's very straightforward. And this is analysis by synthesis. So meaning what you do is you take a current set of parameters P, you render the face with that, get an image out of it, you compute the difference between the renderings and the observations. You get some error. Based on that, you compute a gradient, you do an update step, you re-render again, you continue this update step and optimization step. In practice, you can do different solvers. We're using a lot of like Levenberg-Marquardt solvers, second-order solvers at the time. But basically, you can actually do these optimizations in real time. You can use it in order to reconstruct a human 3D face over time, given some sparse inputs from RGBD sensors. And it turns out you can actually do this even with, so this was 2015 when we did this, and then 2016 we even realized, oh, you can do this even without the depth data. You can go ahead and just take RGB data as input. So with RGB data as input here, you have here the video feed, right? And now what we want to make sure is that every pixel on the face, so every pixel here is ideally matching with every pixel here. That's the ideal scenario. And of course, we're trying to stay with, or we're staying within the parameterization of the face model. But basically, the idea is when you do this optimization, that at some point when you overlay this, that this is looking identical. And the more identical it looks, or the closer it looks, the better job you've done in the optimization. And this also turns out you can also do this in real time. So in this case, we're using a Gauss-Newton optimizer. And based on input video, you then get in real time the 3D reconstruction of the face. You also get the respective albedo and lighting parameters. And this was 2016, right? So there's no deep learning. This is just pure graphics. It's like inverse rendering. We have an image formation model. We do a bunch of tricks how to optimize this, but we get a relatively good 3D reconstruction of the face here. And this was this paper face to face. Well, linked to you mentioned it already. This was one of the papers that was relatively big at the time, because the idea is once you have the face reconstructed, you can also manipulate the face. So I can now take this 3D reconstruction and can change the face parameters. And just on this video, I just render a different face on top of it, right? And this is what face-to-face did at the time. And this is what you can do here in real time, right? So you have here a webcam standpoint, we're tracking his face, and then we're rendering here a different face on top of the original video, right? And then you can manipulate this whole thing. This is a pure graphics application, right? There's again no diffusion model, no networks. It's just rendered on top of it. It's blended with the rest of the face, and you can change the face at the same time. And we thought this was really cool and was really interesting. And it's kind of a precursor to generative models in a sense. Just the little problem what we had is we couldn't change that much. The only thing that we could change is the face part. So the rest of the video was completely fixed. And the question is, well, why is that? And the reason is this PCA-based face model is just a really small part, which is kind of annoying. And why is that so? Well, the problem is if you're doing this with a PCA, you can only do this for relatively smooth and similar surfaces. If you're doing this for complicated shapes, if I'm going to give you, I don't know, like 10,000 models of 3D chairs, and do a PCA on it, then you're getting not necessarily a very good space of this because the transitions are discontinuous, right? And it's not going to work this way. So, but the thing is, we would like to add the detail. We would like to have hair, we would like to have the mouth, the eyes, and all these kind of things we would like to have, because then we can also have an avatar that we can reanimate and change the respective images. And we thought, well, what's the easiest way to do it? The first thing is we have to get rid of this PCA basis. The PCA basis is not so good for it because it's a linear basis, but what we want is, we want a nonlinear basis with discontinuities, with more flexibility, more expressiveness. And we've been working on this for a while, and we are not the only ones who have done this. So the idea is basically you're changing the PCA basis with a learned basis in an MLP, right? And this is, everybody knows that. I'm just trying to have a different interpretation how I get there. What you can do is, right, you just think about an MLP as the basis function and the latent space of this MLP as the parameters of the model, right? So, and this is something that the Steve SDF paper did for shapes the very first time. They used this auto-decoder structure, and there have been many, many follow-up works since then. And one thing we have been working on was, we've been working on doing this for deformable surfaces, in this case for bodies, but you can also do this for faces. And the way this works now is you have basically two MLPs. One of them is the basis functions for the shape. The latent code defines the parameterization. And then you can also do this for deformations, in this case poses. And then you have a different MLP that just is a deformation field on top of the first one, just in order to look at the coordinates. And then you have two, and if you're training this on enough data, right? So during training time, you're training the MLPs respectively. And during inference time, you can then change the shape in the poses and then kind of reanimate or change the identity between the different people. You can also do the other way around. You can also take such a model, keep the MLP fixed, and then if you have a given point cloud, you can fit this latent code to the respective point cloud. So it's kind of the optimization with these parameters P, what are just these parameters P are now latent codes, and the PCA is being replaced by an MLP. Again, nothing fancy. I think a lot of people have seen this in all kinds of flavors. But now I want to show you how we do this specifically for humans and for human faces. So how do we do it? We call this a face NPM, so neural parametric model, right? It's this nonlinear basis essentially what we will use. And the way you're going to start doing this is you always start with some data. And in this case, what we do is we want to do this for faces and heads. So we want to get 3D scans of human people. So let's just assume we have these 3D scans. I'm going to talk about it in a second how we get there. But let's say we have these 3D scans. What I want to do is during training time, I want to take different people in different expressions, and then I want to optimize for an MLP that parameterizes expressions and identity respectively. I have the respective latent code for these MLPs, identity and expression. I want to make sure that these are orthogonal, meaning that they disentangle. Like if I change the expression, I don't want to change the identity. And then what I want to do is I want to learn this latent representation such that when I change these ones, I can animate and traverse the parameter space of these models. And again, what the key of this is that you essentially want to make sure that expressions and identity don't interact with each other. So you want to have they need to be disentangled. If this was not disentangled and you just use like a regular DBSDF or so here, then the whole point would be mute, because if I want to track one specific person, by tracking that person, I would also change the person. I would not just change the expressions. So this is very critical. And I'm going to show you also how exactly we make sure that this happens. But think about it for the time being. We just have two MLPs, one for expression. That is essentially a deformation field that maps back into the canonical space. In the canonical space, we have a shape MLP that predicts a signed distance field. So this is signed distance rooms. And then the ID and the expression parameters allow us to parameterize the whole thing. Yeah, and then at inference time, right? You just go ahead and take these MLPs. You have a depth observation. You keep the MLP itself fixed, and you just back propagate through the network and optimize for the latent codes, and then you get the respective 3D reconstruction. Yeah.
So just wondering, so why would you have a continuous representation for identity? So alternatively, couldn't you just train like one MLP for each person, achieve the same result, or why would you want to change them the second?
Right. So if you have this point cloud on the right hand side, right? This point cloud is very sparse. So this point cloud is missing half of the person. So I need to have a generalized model right now that I can fit to it in order to kind of figure out how the person looks like. So I need to have a generalized basis across people in order to get the reconstruction right.
I see.
So this is generalized across people, basically. Yeah. So if you did this like you said, and you had like one basis for each person separately, I need to have training data for this specific person first. But I don't have it. I've never seen this person right now.
So this also works on scene, because there's somehow a combination of.
Exactly. So you interpolating in a sense between your data set of people, so to say, if you're thinking about it. Well, ideally you can also extrapolate, but like as with many generative models, it's pretty difficult. And I can show you how this looks like. It looks like this. So these are samples from our parameter type model that we just take latent codes, and these are respective samples that our model spits out. And you can now interpolate the shape codes. So this is when you're just changing the ID code. So this is between people, you're now interpolating, and you're getting different 3D shapes that ideally look all like people. That would be ideal. And they all have a relatively smooth transition between them. So again, for faces, this works because they are relatively, well, the face itself is smooth. And so on, yeah. Well, PowerPoint is struggling with displaying the videos, but we have this great animation. This is in PowerPoint. So, amazing. Okay, anyway, so yeah, but you can see it. So for the most part, this looks pretty good. The hair is a bit challenging still, right? It's a bit over smooth. Hair in itself is tricky, but at least we have a pretty good basis function. Okay, here we see the expression parameters that we change. Again, this is in principle all synchronized, but the idea is that if I'm changing the expression parameters here, the person stays the same. It doesn't change the person, right? So if you look here on the left, you're just changing the person's expression, but you're keeping the person the same. And this is through the design of this latent space. Okay, so now I have to talk a little bit more detail. Like this is actually not so easy to make sure this disentanglement happens, because if you do this naively, everything will be, will be a bit messed up.
So
yeah.
Can this handle glasses as well?
Or
other earrings or something?
Yeah, so it in theory, yes. But the problem why we don't have it, we try to remove the glasses during the scanning. So our training data doesn't have that. And the reason is simple, because the face geometry, the scanners, they don't give you good geometry for the glasses. They give you good geometry for the frames, but not for the glasses. So the model in itself would do it, but the data doesn't have it. So if you're looking how we did this specifically, so now what's important is basically in order to train that, and you want to have the disentanglement, you can't just have independent shapes. So now what you have to do is you have to actually establish, first of all, you have a semantic correspondence between the different scans. So what you need to know during the training data, that one person and the second person, when they make the same or when they make different expressions. And the way we do this is we have in total 23 fixed expressions that we're making. And during scanning, we're telling the people which expressions they should make. So everybody makes the same 23 expressions. And we show them how it should look like, so we want to make sure this is synchronized. Right? So here we see two, neutral, and one where they move them out a little bit to the right. And now what we need to do is we need to find a registration between the different people and between the different expressions. And that's important because we're training these two MLPs such that they can be mapped back to the canonical pose. So we need to know the deformation field ground truth when we do the training. And this is actually the hardest part of the project. So what you need to do right now is you need to, well, between one person, you need to non-rigidly register these two people, these two expressions. But you also need to do this between different people. And that's actually not so straightforward. This actually took Simon, who is the main student here, this took him like quite a while actually to get this to work. In this case, it's basically a non-rigid ICP that happens, but you do this with a high fidelity scan, and then you have a unified mapping between all people and all expressions. We also do a little bit more on the MLP side. So actually what we do is we don't just use one MLP for the shape. In fact, we use a local ensemble of MLPs. And what that means is we basically take phase key points, and for each of these key points, we have a local MLP basically. And then the output is a signed distance field, but it's an interpolation between the nearest MLPs you have on the surface. And this one we tried out. So we had this compromise, rather one big MLP versus multiple smaller MLPs. The multiple smaller MLPs worked significantly better because it gave us a better parameterization of the shapes. Okay, so we have this, in fact, we have more smaller MLP codes. Yeah.
Yeah, one more question.
Yeah.
So I think currently the training data is kind of perfect because you have samples for the ID and also for the expression. But have you thought about, for example, we have just one ID but different expression, and if they can share some information across expression and across ID, something like that.
Yeah, we thought about this. As soon as you do this, like you're entangling expression and shape, and then it doesn't look so good anymore. So the key is really you need good data for that. Otherwise, this type of method doesn't. And in a sense, we're kind of following up what people had been doing originally on PCA-based models like Flame and Bazel and these kind of things. So people had been doing that too, except they didn't have a neural basis what we do.
And does that number of local MLP ensembles, can you think of that as sort of the musculature of the face, it's independent control?
Yeah.
The face we would want to have different representations of the muscles?
So this one is just for the different people, but it's not for the expressions yet. So we thought about exactly what you thought. We actually wanted to model muscles, but we realized this is super complicated. So in all fairness, this doesn't model muscles. It's not even close to an anatomic model what we're getting here. We would love to get it, but yeah, it wasn't so straightforward. Yeah, sorry.
We have such perfect training data. Your model only interpolate between among your training expressions, but not generalized to fancy.
Yes, so it can only interpolate between training expressions, but the idea is these 23 expressions are selected that it covers all face motion, basically. Like there's like databases that tell you how to do this to make sure all muscles are being activated, basically. So this is large enough. You can, in theory, also extrapolate to some degree, but if you go too far away, it wouldn't work. But for like common human expressions, this is enough to cover. Okay, so this is for the shape, and then for the expressions, we only have one MLP. We tried also local MLPs for the expressions, but we noticed like a global one here worked better because you need global consistency. Otherwise, you have like also asymmetry in the face and stuff like this at some point. So this just worked better. So we have multiple small MLPs for the shape and one large one for the deformations. Yeah, and then you basically have you have the ground truth from the registered ground truth correspondence between the people, and you're just training the whole thing end to end. And in this case, when we started doing this, I think we trained it on the very first time we started doing this was like we trained this on like 90 different people. 9 different people, 23 expressions. That was the first experiment we had. But we noticed, okay, we need more people. And this is part of the thing. What I haven't talked about is how we get the data. Well, this data doesn't exist online. So like nobody had this done before and published the same data. So what we did is we built our own scanning setup. So this is a little setup. So you see here, this green circle on the top is a little motor. There's 2 phase scanners attached to it. These are RTEC phase scanners. So one here and one here. One is looking upwards and one is looking downwards. These one, they cost about $20,000 each. So there's roughly what you can buy with a reasonable amount of money and gives you pretty good performance. These are structured light scanners. The RGB data is pretty bad. It looks like this. It's not great. And the geometry is pretty good, except maybe the hair could be better, but the rest of the face, the teeth, and so on looks pretty decent. So this is like, I would argue, among the best face scans that currently have been done in the academic world. Okay. And how does it work then? Well, so the people here see the respective expression they should make. And again, this is important that they show that. And then what you do is you go ahead and press a button, and then this whole thing moves around you. So it looks like this, right? So this whole thing goes around you once. Person sits on this barber chair here in the middle. You have to sit relatively still. There's a non-registration pipeline, but it's okay if you move a little bit. But yeah, pretty much try to stay still, and then you get one scan. And then we repeat this process 23 times for one person, and then we put the next person. Yeah, again, scans look something like this. The left-hand side is me, right-hand side is Simon. So these are the raw scans without any post-processing or whatever you're getting. This is just after the registration, but it's not any like mesh cleanup or whatsoever. Yeah, in total by now we have scanned, it's not quite up to date, these numbers here. But in total, we have scanned over 500 people right now. We try to have a reasonable diversity. We're really struggling on this one because we also Technical University. We try to have different gender, different diversity ratios, but this is roughly where we are. We have over 10,000 scans right now. We have 1.5 million verses per scans, and we have, yeah, I don't know, like 800K frames or so. And you see for every person, right, you have multiple scans in the different expressions respectively. Okay. So, and based on this data, we now train our model. So here we see, these are the identity reconstructions. You see the left-hand side is a point cloud. You see flame and basal. These are the standard models you have, that graphics people use for the most part. You see our reconstructions and you see the ground truth. And what's interesting about it, so this parametric model, there's no quote-unquote generative loss, right? This is not a diffusion model. It has no GAN loss. But it's actually pretty good at doing the reconstructions here, given that it's just trained with this auto-decoder style. You still see there's a bit of a gap, right? You see the hair, for instance, here is much more over-smooth than here. Like there's a bit of a gap. But we're okay with that. For us, this was good enough. Not saying this is solved, right? There's still a lot of things on the hair, but it's pretty decent compared to what other people had before, basically. And the same thing, you can reconstruct expressions and so on. And you have the point clouds, you have the flame models, you have the basic face model, and you have ours. Again, you see the hair. Hair is a challenge, right? The hair is a big problem. Even though it's not good enough in the ground truth, we can't even reach the ground truth yet, but the rest of the face is much better than what people have.
Do you use a separate local MLP for the hair?
No. Well, okay, so there's a localized MLP that is close to the hair, but there's not one specific to the hair. I think the one thing what we thought a lot about is whether we wanted to use kind of a neural parameterization for B-spline or so, and then have these guide strands what people do. But then we realized, well, the parameterization becomes very complicated very quickly, and then we did, at least for this first version, we didn't do it. But I think there's a lot of things that are missing. Actually, you could do better there, especially for long hair. Okay, so yeah, for geometry, we were actually okay with the results here. The big question right now is how do we get appearance? Right, so we don't have color yet, so we wanted to figure out how we get that in. And well, the idea is pretty straightforward. We just do similar what the PCA-based model did is we just add another MLP for the color. Right, and this is what we have been doing. So this is called mono NPHM. This is from this year's CVPR actually. So here the idea is you have. This is what we had before, right? We have expression and geometry. You have the respective MLPs, you have the latent codes, and you get an SDF here as a prediction. And now what we do is we simply add another MLP that has here appearance codes and it has the appearance here and predicts an RGB value respectively based on the geometry. And what's important here is actually we want to have an entanglement now with the RGB. So the point is, if I'm gonna optimize for the RGB here, I want to backpropagate and also get the expression in the geometry codes. Because the whole point why we want to do this is actually not to have a photorealistic avatar, but to be able to fit this model to RGB input. So in other words, I want to go ahead and give me one image, or maybe multiple images. I have a re-rendering loss in RGB, and I want to get all three codes here for my parameterization, and this way get a 3D reconstruction of the face. Okay. There's a couple of more things we're doing here. I'm not going to go into all the details. There's also some lighting modeling. We're using some sort of harmonic shading and stuff like this to make it work better. But in principle, what we have is we just have three codes now. We have three MLPs. These depend on each other. So if I'm optimizing for RGB, I'm also going to get the other three, or the other two. And yeah, this is how it looks like. This is the RGB model, right? So you see, it doesn't look photoreal, but it looks like a bit cartoonish, but it actually looks pretty decent for what we're doing here. And again, there's no generative model, right? There's no diffusion model or so. This is literally just auto-decoder style. And yeah, so I want to show some of the results of this latent representation because I think it works remarkably well for how simple the method is. So this is these are geometry codes. These ones here are the appearance code for a fixed geometry. And now if you're changing both of them at the same time, you basically have the respective RGB on top of it. Yeah, and then you can also change expressions, right? So if you're changing expression, it looks like this. So again, they don't look super photoreal. We're not quite yet at a real avatar. But if you remember at the beginning, I showed you this basal flame model that had basically just some albedo baked on top of it. I think this looks already a lot better, and you can do a lot more stuff with it. And the stuff what we wanted to do with it is, again, it's not make it look realistic. I mean, maybe that's something we still want to do at some point, but we want to go ahead and fit this to an image or multiple images. So here you see multiple RGB images, and the only loss you're going to have is an RGB re-rendering loss of this model. And then you're getting the geometry because you're optimizing for the latent codes of the geometry and expressions. And this optimization looks like this. This is actually the optimization. Right, so it re-renders the whole thing, and you see at the end of the day, jitters a little bit around, but it figures roughly out how to align this whole thing. And this is just a standard SGD optimizer that tries to optimize for that. And then you get the geometry for free, right? So here you see this on a video sequence. This is a single RGB video sequence. So you see the RGB reconstruction. You see the geometry reconstruction on the other side. Okay, so now, again, compared to what Basel and Flame were doing, we already have a lot more, right? Okay. And these are the geometries you're getting. Not perfect, but I think it's already a pretty important step here. Okay, so now what we can do is we have a parameterized model. We can optimize and reconstruct for the respective face geometries. Now I want to go a step further, and I want to tell you how we make this one look photorealistic. This is the thing missing. So the photorealism is missing, right? So how do we get there? And the big challenge, what we realized, well, we're very pragmatic here, and for all of the stuff you've just seen, we just used these RTX face scanners, and the RGB data itself was already pretty bad. So this one you got from, this model you got from the RGB data from the RTX scanners. That's also part of the reason why it didn't look that great. So we needed better RGB data. And what we did is we built a setup specifically to capture RGB data. And the setup looks like this. So this is a setup that has 16 cameras, and they're all front-facing. So each of these cameras, they recorded 7.1 megapixels each. They have 73 frames a second. I was really keen on having a higher frame rate to get like eye blinks and eye motion as well. And they all have global shutter, so they're pretty decent. And they're synchronized with a global trigger. And 16 cameras is pretty much what you can still stream in real time to a server with current motherboards and stuff like this. So basically take your favorite node of your compute cluster with GPUs, get the GPUs out, and then get a bunch of network cards in and try to stream this one in real time. This is basically what you can still barely do with a motherboard capability.
The illuminators?
This one is all static lights. So there's no changes, but these ones are just like in order to make sure we have relatively short exposure times. Does it answer? Or?
The color temperature.
I don't exactly know what we've done. These were just the off-the-shelf things we found in a construction store. And yeah, this was basically done all by computer scientists, so we didn't have any clue beforehand. And so we built this aluminum scaffolding. The cameras, we knew what we wanted. And for the light, for this project, we just took static lights. But we have a follow-up project we're doing and want to change the light now, of course. I mean, it's just, we want to build kind of a light stage for faces. So yeah, I don't know exactly what temperature we're using, but the thing is pretty bright. So you actually have to get used to it a little bit. It's like a TV studio in a sense. Okay, so recordings look like this. So these ones, PowerPoint struggles unfortunately with 16 videos, so it lags a little bit behind. But these ones are the recordings, right? So they have a grayish, whitish background. You're getting this one recorded at 73 frames a second, and you're getting pretty decent data actually. So I want to show quickly the resolution also. This looks like this. So you can actually zoom in quite a bit here. So you can actually get up to the fidelity of the hair, and you can go pretty close. Also, the frame rate is pretty important, right? So we wanted to get stuff like this, so you can do, I don't know, like a shampoo ad or so. But yeah, I mean, yeah, this is a very tricky sequence actually. This is one of my favorite ones. I wanna eventually be able to do. We can't do it yet in fairness, but I think this would be cool, right? If you can reanimate the hair and stuff like this afterwards, I think that would be really awesome. Okay, so in total here, the thing what I didn't tell you, we built both of these scanning setups at the same time. So one of them was for the geometry, and one of them was for the RGB. And we captured also with a bunch of predefined sequences. So we wanted to cover a wide range of motion. Like also we have some audio recordings with phonemes and stuff like this. So we're having these type of recordings here in this multi-view data. And we have a little bit less than in the other setup because this setup was a few weeks later done. So the first few recordings we just had for the geometry, but the majority is actually perfectly synchronized. And we also have the registrations between the two. So we have both of them. So we have actually now RGB and color map basically. Okay, so yeah, so we have a lot of recordings, it's a lot of data. So one recording is like, I don't know, like a terabyte per recording roughly. The fun thing is we try to do multi-view stereo reconstructions for like one frame, right? You have 16 cameras, you run Colmap. And turns out, right, if you run Colmap on the raw images, it's very different than if you compress the whole thing. So if you just run an H.264 encoding on it, you're getting very different results on Colmap. So the low-level features really matter here. So what we did is we have the raw data. We also released the raw data right now, which is quite of an endeavor to use it because you have to download a lot of data now. Okay, but let's talk a bit algorithmically right now. So we have a lot of cool data. How do we get there and make something useful out of it? So the task, what I want to talk about is first a reconstruction task. So in this task, we want to have 16 video sequences input, and we want to get this one on the right as an output. And reconstruction means it's not yet an avatar, but it means you can just get a 3D representation from it. You can do novel viewpoint synthesis, but you have no control over the person yet. So this was the first task we wanted to do. And we thought, well, this is essentially what dynamic nerve methods are doing right? So you want to do novel view synthesis method, you want to reconstruct a 3D nerve representation. Once I have the radiance field, I can then like just parameterize it with respect to time, can go through it, and I can go ahead and re-render it from various different viewpoints. And it turns out this is actually not so straightforward. And the reason why this is not so straightforward is the way MLPs work in a nerve representation. So the problem with a nerve is, so in principle, you would think, oh, the more images I throw at a nerve reconstruction, the better it works, because I have more constraints. So hence I get a better 3D representation. But the problem is the MLP has a capacity limit. So eventually you run out of capacity in the MLP. So if I throw more data at it, actually at some point it gets blurry because you can't optimize it anymore. And just scaling up the MLP is not so straightforward. At some point you have like vanishing gradients and the whole thing doesn't scale anymore. And this is a really big issue. Right? That's why people do like, hierarchical nerve representation. I mean, you've done a lot of this stuff. Like these kind of things is like, you can't scale MLPs infinitely because they're gonna run out of capacity. And you get vanishing gradients if you make them larger. So the high level idea is we have to find a better composition in 3D. So the first thing what we thought, well, I mean, this is straightforward. We just map it back to canonical representation. So we have some sort of dynamic 3D representation first. We map this one back to canonical representation with the deformation field. And then in this canonical representation, we just locally map the stuff, add the stuff that you couldn't express with the deformation field. Like when you open the mouth, for instance, you see new stuff that has to be added to the to this dynamic representation. And now the idea of having just a single nerve representation, we also split it up into different nerve representations. And the way we split it up is we're using a static template. So basically, we want to make sure every expression here has a different, every expression here basically maps to a different separate nerve representation, right? And that means by different template, every template ideally should match to roughly some sort of expression. That would be the ideal situation here. We don't quite get there, but roughly this is how we want to distribute the nerve capacity. Yeah, and then we want to learn how to blend between those. And we want to do this all at the same time. Okay, so let's talk about the method in detail. Okay, so I mentioned you want to use a nerve representation. So how does nerve work? Well, we have kind of like a volumetric representation. You shoot rays, you sample these rays, and each ray has radiance and density values. Okay, and then you integrate over them and you get the final renderings. So the first thing what we do is we have an MLP for the deformation field. This is very common what other dynamic nerve methods do as well. So this maps you back to canonical space. And then what we do is we use basically an instant NGP for each of the expressions separately. So we use this ensemble of hash grids basically that encodes the radiance fields. Each of these hash ensembles gets you a feature as an output for the respective location you query it for. You blend those features with a linear blending function. This function is also learned. So you learn these weights. And then you run those ones, these features that the blended outputs, you run through an MLP and you get your density and color outputs at the end of the day. And the whole point is you want to make sure during training that the expressions are getting split up through the different hash ensembles. And so when you train this, you just start basically training with some parts of a sequence. You only train this one for now, and then you add the other ones and you're adding more and more flexibility. And the way we're training it, basically, we're making sure that based on the expressions that you're making, it splits it up across. And you can show that afterwards, that each of them are responsible for certain expressions. Yeah, and the whole thing is trained end-to-end. We're getting a 3D representation out of it. And we have now a reconstruction of our recordings. So these are a few samples that we're having, right? Again, these are not avatars. These are just nerve reconstructions that you can render from different viewpoints. And it was a surprisingly difficult task because we thought, oh, we had really good data and we want to get good nerve reconstructions. But it turns out the good data makes the problem harder because you need more capacity. Okay. Yeah, a few more results here. So yeah, of course you can zoom in, right? And I think, yeah, I don't know, quality-wise, I would argue this is pretty decent. Now, big question is, how do we animate the whole thing? Now we want to add not just the reconstruction and how we make an avatar out of it. That's the missing piece now, right? And we thought about this for nerve for a while. How do we animate this nerve now? So we wanted to originally use these basis functions or these base templates and figure out how to animate them with some sort of like blend shape model or something like this. And then what happened is 3D Gaussians came out. And it turns out with 3D Gaussians, you can do this much easier. Because the only thing what you have to do now is instead of a nerve reconstruction, you take a Gaussian reconstruction. And then you have an explicit version of it and you can move them around. So you compute this rigging. And that's what we've been doing. This was the Gaussian avatars paper. It feels already old, but it will only be presented at CVPR next week. So the idea is basically we started the flame model. And this flame model, this is not just the flame model. You see, this is not like a flame model, but it looks a little bit different. So what you do is you want to optimize for offsets on the flame model to match the geometry better. And then you figuring out a parameterization that rigs the Gaussians relative to the space geometry. So the points live on top of this flame model. They live in the local coordinate frames of the flame model. This is with linear blend skinning. They are being rigged to it. Then you have the Gaussians and you can re-render it accordingly. And the idea is once I've optimized this Gaussian, once I've optimized the geometry, as well as the Gaussians relative to the base model, I can then go ahead and change the base model and then get a reanimation out of it. That's kind of the high-level idea. And there's a lot of details how exactly to make this work, right? Like basically, Okay, the rigging needs to be working out how to make the smooth transitions between the rigging so you don't get these overfolds and stuff like this. But the whole point is essentially you can optimize this whole thing end to end. And eventually what you're getting is this base flame model, and then you can animate the whole thing at the very end of the day. And this looks like this. So here we see the very same example what I've shown you at the very beginning of the talk. We have a flame model here. We have here these little sliders, what you saw at the beginning. These are the expression parameters. So now I can change my flame model. That changes the Gaussians on top of it. And you're getting results that look like these. Right. So this is my avatar now. So now I can fully control it. I have pretty good re-rendering capabilities. And what's nice about it, this thing works in real time, right? Okay, not the optimization, of course, but the re-rendering and the animation works in real time. And I think that's pretty decent. Yeah, this is the underlying geometry. And you can change the poses. And you can also use different inputs now, right? I can go ahead and have here a source actor. I track this guy's face. I take the expression parameters and the pose parameters and move it over. And this is what you're getting here. And again, this works in real time now. And comparing it also with what we had before with like face-to-face and stuff like this, this has full rigid control of the head, right? You can just arbitrarily move it around. You can put this into a game and you can animate this whole thing in real time. Okay, so there's one little issue. I'm telling you a lot about these neural parametric models, and now I'm using a flame model to animate this thing. And you might say, well, that's dumb, right? Because you want to have better geometry. And it turns out, like, if you're making large motions here, this will have some blurring artifacts. And the reason is simple, because the space model here doesn't fully match the geometry. So the argument what we're having is, well, if you could match better the base geometry, you would also get better Gaussian animation out of it. So now what we're thinking is, can we go ahead and taking this as a base model, the neural parametric model. So this NPHM, right? So these are the trackings with NPHM for the RGB data that we're recording here. And they're not 100% perfect, but they're way better than the flame model, of course, right? Because you have more parameters to fit the whole thing. And it turns out you can now use that one as a base model to model the Gaussians as well. And this is some ongoing work right now. It looks like this. So here's the input now, and these are the avatars from the output. And this is like another level of quality you're getting with this. Right? So you see here, like if you look at even the mouth or so and the teeth, I'm arguing this looks pretty good. Yeah, so this is like the best avatars we can do right now, I think, pretty much for faces. Okay, so I have a few more things. So now, right now, I've talked a lot about faces. The question is, how do we make this whole thing work on humans? Right, because I want to have a full avatar, not just the face. So now it's a little bit tricky, because now we have to get data for humans. So how do we get data for humans? Well, we're building a capture setup, and by building, I mean we're renting one, because building it is very costly. So this is a paper also from last year at SIGGRAPH. This was done with our startup Synthesia, and so we rented basically out a capture setup, and this is the capture setup we looked at. This is called Deus Ex Infinite Realities. This is a capture setup in Europe, and this is a company that builds these things. So they have actually 160 cameras now. And each of the cameras have 12 megapixels. They recorded 25 frames. And per frame, you want to get RGB and the ground truth meshes accordingly. The ground truth meshes, these are just multi-view stereo reconstructions. But if you have 160 cameras at this resolution, it turns out you can do pretty good multi-view stereo reconstructions. And yeah, so basically, you can get pretty good data with that. You can zoom pretty closely in. And what we did is we hired basically a bunch of people as actors, because we thought if we have a setup like this, we also want to have not necessarily computer science people dancing in there. And we have people that we recorded. No offense to the computer science people, though. I think we're cool. We're wrong, by the way. Okay, so we have in total, we have only eight recordings here. Sorry, 8 reconstructions. Recordings, we have more. We have 8 different people. And yeah, this is actually not so straightforward to get this. Just to give you a bit of a sense of the data here. I mentioned before, 16 cameras, you can still stream in real time to a server. This one, nah, not so much anymore. The way this one works is you have these 160 cameras. Each camera has about 10 terabyte SSDs on the camera. So it record for like 5 minutes, and then you download the data for a day. So tricky, not that easy. But data is amazing. This is the best data basically you can get. So this is very similar to what the Facebook people do in Pittsburgh. And it's become a pretty costly process though. Okay, so yeah, we have these people that we recorded, these 8. We try to get a reasonable diversity, both in terms of gender and ethnicities. And yeah, these are basically actors that we actually have. Okay, so what's cool about it is, so you're getting pretty good stereo reconstruction out of this actually. So this is a stereo reconstruction. So you see the geometry here. This is a per frame reconstruction that you're getting. And it turns actually out this is a pretty intense compute game you have to play here, because you have to run a multi-new stereo reconstruction for every frame, for every time step. This is similar to training large models. This is really crazy, but this is something we've done and also released with it. So, people can actually already use that. We also played a little bit around how to do the reconstruction with it. At this point, I'm not going to go into all the details here, but basically what we're doing is we're having also a splitting in terms of the capacity of the MLPs here across time. So this is like a TensorRef-based representation. In this case, we have multiple decompositions, and they're computed adaptively based on the convergence. So the way it kind of works, you get n frames, and you add another frame. Is it still working? Add another frame. Is it still working? And eventually you run out of capacity, and then you just start a new segment. So it's super brute force. It's super slow to optimize. It's also super slow to render. So it's not very efficient, but the quality looks pretty good. So if you're doing this, you get a reconstruction like these ones. I mean, they're not 100% perfect, but this is pretty good in terms of the respective reconstructions you're getting.
Artifacts on the boundary, it's due to the masks.
Yeah, it's a mask. They're not perfect. And there's another issue with it. What we have here is so the problem what's missing here is the lighting is not figured out yet. So basically the lighting is all baked in. If you figured that one out, then it would look a lot better. And I mean, that's what we're trying right now, right? But I think the reconstruction itself looked pretty decent. Question now is again, how do we animate the whole thing? Well, this is something we haven't done yet, but I mean, a lot of other people actually have worked on this. So there have been people, this is from Yevin Leo's group, from Tsinghua. So they have worked on Gaussian animations for humans. Actually, if you see, they use our data here to drive their avatars. And they get pretty decent results with that already. Yeah, these were their reconstructions, basically, what they're getting in their animation. So now we have already an avatar for humans as well, in a sense. There was one other work that was also, I think, pretty cool. This is from Wojciech from Justus T's group, and this was an internship at Meta, I think, at the time when they did this. So this is from Meta's data, by the way. So they have similar data in a sense internally, but very similar in terms of they have a lot of cameras, right? And then they get these avatars here. So also you have a base model, right? And then you have the default the Gaussians on top. Okay, so this is roughly where we are. This is pretty much state of the art what we can do. And you might have noticed, I haven't talked a lot about learning here in this talk. There was not so many people. Okay, we use neural networks like the MLP for the parameterization, but the rest is optimization. It's just pure optimization. There's no generalization at all, actually, except for the base model that we're learning here. So what's missing, right? So this generalization, I think, is the biggest thing that is missing in this specific space, right? So this is what mono-NPHM is doing. This is like this parametric model with a naive auto-decoded color channel. And this is the per sequence or per person optimized Gaussian avatars of diffusion. We have another paper we have at CVPR, it's called diffusion avatars, but it's also not generalized. It's just on one person. And the question is like, how to bridge this gap here, right? I think this is a very fundamental question, actually, how to get there. And it's not that easy. And it's not that easy for many reasons. So one thing what we thought is, well, we're going to have data right now. We just capture enough data to learn a generalizable model that generates you new avatars. And it turns out we captured we in our academic lab, we captured 500 people. Training a generalizable model on 500 people that generates you new people seems not quite realistic. Or in other words, this is not going to happen. I don't know how much the Meta people have captured, but I know they have these trucks. They drive around the US and have these capture setups in a truck, and then they get people into the trucks, which is crazy expensive. And I've heard at some point they have a few thousand. So let's say they are really successful with them, they get to 100,000. I think even if you get to 100,000 people, generalizing to new people is still very difficult. If you're thinking about what current diffusion models do in 2D, this is tricky. So even if we spend all of Meta stock and all of Apple stock, all of Google stock, we're not going to get enough people scanned this way. That one is clear, right? So it needs to be a better way how to do that in practice. However, there also has to be a way to still maintain the controllability. So this balance is hard. So I can show you the other extreme, what people are doing with diffusion models, with video diffusion models. This is a paper from Microsoft. It's called VASA1, it's Microsoft Asia. And what these guys are doing, they're basically training a video transformer. So this is very similar to what Sora is doing, but just trained for faces. And they also have video blocks. They train it explicitly for face models and so on. And they basically generate the videos directly without any 3D notion whatsoever. And they get actually pretty good results. So this looks pretty reasonable. Now, you might ask, well, this looks pretty good, so we're done. The problem is this thing is not controllable. The control here is horrible. And you can't just turn around the head. You can't do this. You can't look around here. This is just the video you get output. So like using this in any graphics engine, combining it with other avatars, merging it together is not working. And it's also trained on a lot of data and on a lot of GPUs, and it's horribly slow. So we are far away from using this in any real-time thing anytime, and the control is not. But the question is, I mean, this looks awesome, right? So now there's a question of how to bridge the gap between these two worlds, between like I have a lot of 3D stuff and I have a lot of 2D stuff with foundation models, how to bridge it. And this brings, this is a thing I have in every talk I'm giving right now. It's a question of what data do we use? Well, I mentioned this. For faces, we have like 500-ish right now, maybe a bit more, but roughly in this order. That's not going to be enough. For humans, there's this from Shanghai Tech, they have this super cool data actually. I think they also have like hundreds, maybe 1,000 scans by now, I don't know exactly, but they have full humans. This is the largest academic version that I know. This is really awesome. This is this DNA rendering, really great work, but also not like hundreds of thousands, right? So now the big question is, what data do we want to use? Well, now we have this little chart. And I don't know, I posted a couple of times on social media. I think this is very interesting for research questions, generally speaking, not just for faces in this domain. For other domains, this is the same thing. So we have 3D data that has thousands of samples, what I just said, maybe tens of thousands if you spend on the order of billions, right? So you spend millions to get thousands, and you spend billions to get basically tens of thousands. For multi-view data, you can get a bit more, but it's still the same order. For videos, you can already get way more, right? If you crawl YouTube, okay, I wrote millions here, but I'm pretty sure that Sora is trained on billions of videos. I think millions is not enough here. Images, you definitely get billions, right? Like, I mean, Lion and stuff like this has a couple of billion of samples. And for text, you have trillions. So, right, so we're getting more training data this way. Little problem is you're getting less supervision, right? So here's the tricky thing. So each sample here on the top has a lot of supervision, and the bottom it has not so much supervision. Like, just from text alone, generating like visual outputs is not going to work, right? It doesn't have the supervision. So you have to combine it with other modalities. And I think this is a really fundamental question for both academic and industry research right now, how to navigate this route here. Like how do you use, what data do you use, and then how to leverage it. For instance, you could imagine things, what people are doing a lot right now, we do this too. So you can have like 2D foundation models, like you take Stable Diffusion, because that's the only one that is good enough and is open source. And then you do score distillation on top of it. So you're extracting some information at test time, so to say, and then optimize your 3D model on top of it. Question is, can you fine-tune these models on 3D data maybe? Can you fine-tune them on multi-view data? And all of these things people are trying right now, or have tried already to a large degree, like multi-view diffusion models are training multi-view data then. People are trying to all kinds of fine-tuning tricks to make the diffusion lines of work better, and so on. So there's a lot of work, of course, going on, and it's still interesting, but I think this is, to me, this is very interesting, like how to navigate this. And I think this will define our research and where we spend for a while. I mean, I've shown this to you for faces, but I think this counts for pretty much all kinds of like any 3D/video prediction and so on. Okay, so with that, I'm pretty much at the end. I want to conclude these few papers I've talked about from pretty much like the last year. It should be all public. I also want to highlight all the data is public that I've talked about, right? So all the face data, the scans are public, the human data is public, and I hope that people encourage and use this. Specifically, I want to thank my PhD students and all the collaborators who actually worked on it, right? I mean, obviously, this is like not just my work, like, I mean, I'm just here to talk about it, but people who actually do the work, especially Simon, Tobias, so they have done most of the scanning setups in our lab. And yeah, thanks a lot. Thanks for having me. And maybe we can still chat a bit.
Thank you very much for the amazing and inspiring talk. Any questions from audience?
So as somebody who doesn't quite work in this area, I found something that you mentioned about how nerve representations in the neural network form are fundamentally limited in some way. You spoke about how the typical MLPs that you use are kind of small, and just adding more depth or adding more width to these networks doesn't seem to work. Do you have some sense of why this is the case? Because we arguably deal with these kinds of architectures and so many other problems. And so what is so special about the neural rendering problem that makes it difficult to scale neural architectures? Are people actively working on exploring improvements to the basic MLP architectures here?
So first of all, I don't think this is specific to neural rendering. I think this is general. And my understanding, it's basically just about the gradients. So basically, if you have large architectures without skip connections, without unit tile, I mean, maybe there's MLPs with unit skip connections and stuff like this, right?
Sure.
But I think the high-level idea is you just have a standard regular MLP and you scale it up. Eventually, the optimization becomes harder and harder because you have a large amount.
That I can believe, but yeah, why would it not be then the case that the same solutions that have worked in other spaces can also be transported for rendering?
Yeah, I think they would probably work.
Okay.
Just people haven't done it yet. But I think even in other spaces, I think generally speaking, for standard MLPs, I think people have stopped a little bit once they move to other architectures in a sense. Right? Just from a, historically we had resonant architectures, right? So people made sure they can be scaled quite a lot. And then they moved away from MLPs. And then transformers, of course, have the big victory lap in a sense right now, right? So they have different properties again, but the standard MLPs, I would say, generally speaking, are not as investigated anymore. They exist a few things, but just people haven't tried it yet for these kind of applications. And I'm not saying this doesn't work. I'm just saying currently at the moment, fundamentally, it's still easier to just work with more but smaller MLPs and then build explicit data structures around it. And this is very common for many areas. It's not just for here the case. But I think there's many opportunities. I think that people can make this better, and I think some theory papers are already out there that just have to be adapted and implemented, and I think they would probably help to speed up the stuff too.
Thanks for the inspiring talk. It's really interesting. I have a question about, so how far away are we actually from integrating this into the product? Like, what are maybe the biggest stopgaps which enable us to improve this?
Yeah, I think that's a really great question. I think first of all, there's a lot of opportunities commercially. I think the question is a bit, what is the respective business application for it? So, for instance, we have a startup called Synthesia. So Synthesia, the goal is you will make learning videos. So you type in text, and you're going to get a video of somebody out that explains to you certain things that you typed in, right? So we have customers like McDonald's or so that have just such a high throughput of people coming in, so they need education videos how to use certain machines and so on. And the idea is if you have a person telling you how to work with this, then you have more engagement and stuff like this. And part of these things are commercialized, so they work. Synthesia is now 400 people, we're basically profitable, and so there's a really big business case around it. How far you are in terms of making this work for games and movies and stuff like this, I think a lot of stuff is getting there. I think the big missing piece is still the lighting disentanglement, which not that many people have worked on yet. There's like another axis in the setup. Now you need light stages, you need to have more control. It's another dimension. But I think that's going to happen. And also what happened is like all the VR companies, they already adapting this stuff. So Meta and so on, they're doing it. But there's another fundamental thing that I haven't talked about is the whole question is how do you look at the stuff afterwards? What's your display? How to look at it, right? So I would love to have a version of Zoom that replicates this meeting setting. But the problem is I look at it on a 2D screen, so I can't just do it so easily. So I have to also figure out how to put this in VR and AR or so But then, yeah, AR, VR devices, I mean, they're cool, but they're not at the level yet where, like, you know, you have like billions of sales a year. So I think from a prioritization standpoint, I think it's pretty close to make this kind of stuff work in various applications. But the question is also like, you know, how do non-computer scientists, in a sense, how much do they care? How much business value do you add and stuff like this? So, so yeah, we're debating this a lot, and but I think we're not so far away. I think the gap of actually making it work in practice is pretty small right now.
For the lighting composition of the rendering avatar, do you think current data is enough for disentangling lighting from the screen, or are we still needing more data?
So the data we have been captured was always the fixed lighting. So for this one, fundamentally, you can't do a good lighting. So it's not, this one is not enough. That one we know. So the movie industry has also, they have been working on this for a long time, specifically Paul Deberweg. He's like the light stage guy, right? So he's been working with Hollywood for the last, I don't know, 2 decades or so, and build like capture setups where you put a person in and you have different light sources. You just go and have all combinations and you figure out the BRDF of the person. So for the most part, this kind of stuff was done mostly on static people. So you have a person in, you move them in, reconstruct the BRDF figures and hair and everything, and then they can relight it and insert it into a movie. And then you have a bunch of CG artists and they figure out how this stuff gets composited the right way and how it looks good. But that data is also not public, right? You can't get that. There's no chance on earth that the movie studio is going to suddenly release your favorite actor's virtual digital clone. That's not happening. So light stage data public doesn't exist basically. I know that Facebook and so on, they have been trying this too. I mean, they're public about it, but they're also never going to release this data because they're worried about all kind of legal nightmares they're dealing with, right? So yeah, I definitely think for the lighting decomposition, you need also some captures of light stage data. I think you need that, and it doesn't exist yet. So that is a great opportunity. It's not an easy problem because technically what you want to do is for every frame, you want to record all light combinations, but the person's moving. So, so you have to, it's like algorithmically also not so straightforward. And but maybe there's other ways to address the problem also. Like, I mean, there's a lot of people working on intrinsic image decomposition. Maybe you can also use foundation models for that, right? You can also try to extract some stuff out of it. Just think about it, like when you have like stable diffusion or so, can you get a stable diffusion that produces not an image, but each intrinsic component separately? That would already help a lot. And then you could use this as a prior, maybe with SDS or so, and then you could maybe do it on this data. But I think both the data is not enough yet, and both also the methods are not quite there yet. I feel there's still a bunch of stuff.